Hi, my name is Berkvens. I'm from the University of Antwerpen, as been introduced by the assistant chair, and I will present asynchronous electromagnetic sensor fusion in RatSLAM. But the talk will mainly focus on how we try to predict the performance of the various sensors that we used by using the mutual information. I'll come to that. So first, I'll quickly introduce RatSLAM. But since we really used RatSLAM and didn't really change it, you might want to find additional references if you're interested in RatSLAM in the paper, or you can come talk to me later. Then I'll discuss the mutual information that we used, the measurement models of the various sensors. We used active RFID at 433 megahertz, a geomagnetic flux sensor, a passive RFID sensor, and Wi-Fi. Then I'll quickly show the trajectory and go over to the results. So this is a simple overview of the RatSLAM system. On the right-hand side, you see the experience map. This is what comes out of the system. It's a topological map that really is the trajectory as estimated by the RatSLAM system. Oh, and maybe because this is a sensors conference, I'll say SLAM is simultaneous localization and mapping. So you're trying to localize in an unknown map, and you're trying to build the map while you do the localization. That's what SLAM is. And RatSLAM is based on how rats, the actual animals, do this in their cognitive system, in their head. But of course, we don't use actual rats. We use a computer model of their brain, which is the postal network. And again, I'll have to refer to the paper if you're really interested in how that works. We changed the local view network, which is originally modeled with cameras, and we changed that to the 4 sensors that I just discussed. Also, the asynchronous sensor fusion happens by the postal network, so we simply feed in the sensors, and the network itself can manage the sensor fusion asynchronously. So what we did is we created our measurement models to feed into the RatSLAM system, but we tried to establish the mutual information between such a measurement, what it tells you about your location environment. So that's why we used mutual information. This is the standard definition of mutual information. This is how we implemented it. So the P ensemble is the positions in the environment. The M are a measurement at a specific location in the environment, so that you can see if you do a measurement at that specific location, what information do you get about the positions in the environment. So this is the theoretical overview, the complete system, so to speak. But it's difficult to really model every single measurement that you can take at a position, so we use the marginal probability of a single measurement at a position. So this is that formula, where you got, again, over all the positions, but for a single measurement. And then we do some measurements at every location in the environment, and then we try to, by using Monte Carlo sampling, create the mean mutual information at that location. And so that's how we solve for not knowing exactly every measurement at every location. So we use, in our paper, equation 4, to calculate the mean mutual information. So let me go over the measurement models that we used. This is for active RFID and Wi-Fi. The active RFID sensor we used is kind of comparable to Wi-Fi, where Wi-Fi uses 2.4 gigahertz. This one uses 433 megahertz. And what you do is you scan for access points visible in the environment, which you see in the left-hand column, which is access point A, B, and C, for example. This is an example overview of the measurement model. In your database, you collect for every location in the environment what access points you saw and with what received signal strength you saw. And then when you do measurements in the runtime phase, there's 4 possible things that can happen. Either you see an access point at a certain location and in your fingerprint, then you can do kernel matching. Either you see him in the database when you collect your measurements, but you don't see it during runtime. So then we create a penalty based on the received signal strength in a database. You can also measure an access point that you did not see in the initial phase. That's what we call an extra. Again, we create a penalty based on how many measurements we did in the database and the received signal strength in the fingerprint. And lastly, you can also have the case where you know that there's an access point in your environment, but you didn't see it in your initial fingerprints, but you didn't see it either in your actual fingerprints. And again, we create a penalty based on that. When you go to a SLAM system, you don't know, of course, which access point you'll see in your environment. So this is accumulated over time. So when you do your first actual positions in your SLAM system, indicates that those are all separate positions. You have a single measurement modeling that position. And when you arrive back at certain positions, you start creating the, accumulating them using the mean received signal strength. And then, of course, you increase your vector of the different access points in your environment as you see them. Next is the geometric flux. This one we used also separately for each axis. So we use a mobile robot to collect trajectory, where we put a smartphone just separated from the robot, so it isn't affected by the metal parts of the robot. I mean, we just put them in the same position, so we can assume that the axes are independent received, and then we have a heading-dependent measurement. We simply do kernel matching of the signals we already saw and the signals we now receiving, and multiply those. Then, of course, you also need to know a kernel width, and in previous research, we found that to be working out at 2, well, I'm not going to start thinking about the actual unit now. For the passive RFID sensor, this is created by tags that are located throughout our laboratory, and they are all fixed on the ground. And on the robot, we have a reader underneath the robot, and when you see a tag, then you know that you're at that location. If you don't see a tag, you know that you're not on the location of a tag, and that's what is modeled in this measurement model. All right. So then this is our trajectory. So this is a laser map of our laboratory. This is how we drove with the robots. It's a 450-meter trajectory, going up and down and going in different circles. This is a rather complex trajectory to map using SLAM because you're doing loops in different directions of the same location. So you need to know what heading you have, or that you're at least not having the same heading as the last time, so that you can correct your trajectory based on that. And then we also calculated the mean mutual information rate. This is also important, so we calculated the mutual information of our different sensors in our environment based on post-processing. So we already did the measurements, and then we tried to estimate how much information every sensor would give us, and multiply that with the measurement rate. So the mutual information is calculated based on one single measurement, but when you're doing your SLAM system, your different sensors will give you more information per second if they have a higher sample rate. If a single measurement gives you a certain amount of bits mutual information about your environment, if you have a higher sample rate, of course, your mutual information will also increase. So these are the cumulative distributions. What we would expect from this is that on the right-hand figure, you see the sensors going into the 200 to 300 bits per second. Those are the ones we expect to perform better in the RatSLAM system, and the ones on the left-hand side we expect to work worse. So the ones to look out for are number 2, Flux, 5, active RFID and Flux, 8, Flux and passive RFID, and 9, Flux and Wi-Fi. And now you see every time Flux, and that is also because Flux has a very high sample rate. So these are the 10 sensors. Again, the 4 sensors individually, and then in combinations of 2. So you've got active RFID on 1, 2 is Flux, 3 is the passive RFID, 4 is Wi-Fi, 5 is active RFID and Flux, 6 is active RFID and passive RFID, 7 is active RFID and Wi-Fi, 8 is passive Flux and passive RFID, 9 is Flux and Wi-Fi, and 10 is passive RFID and Wi-Fi. And again, you see that the ones you were here on the right-hand side, 2, 5, 8, and 9, create visually the better topological maps of the environment. Now, that's of course something that not only qualitatively, we also try to quantify that using the mean error of the trajectory compared to the ground truth that was created using the laser system. And we also see that the 2, 5, 8, and 9 do have the lowest mean error in this scenario. But on the other hand, you also see that the one we expected to be highest, which is 8 and 9, are not exactly the lowest mean error in the list. So it is, in conclusion, we show that the mean neutral information does give a general idea of how well a sensor will perform in the RatSLAM system, but there are discrepancies in specific cases. Now, what we want to do actually is also study different measurement models so that we can compare using the mutual information if your measurement model gives you a better, gives you more information using a certain sensor. And we also use the conditional entropy now rather than the mutual information, which actually gives you the same information, but instead of telling you how much information the sensor gives you with a single measurement, it tells you how much ambiguity is left after doing the sensor. But this makes comparison in different environments easier because you go to 0 now instead of 2, an arbitrary number which is dependent on your environment. So, thank you all for your attention. I'm happy to take any questions now.